All right, last example in these quantum notes, the deBroglie wavelength. We're asked to calculate the deBroglie wavelength for an electron and also compare that to the wavelength of a photon. So both of them have the same energy. So imagine you have this photon. We'll call that, here's the photon picture here. It has an energy of 25 electron volts. And then imagine you have an electron, right, that is moving at some speed. And it has an energy of 25 electron volts. So we'll first do the easy part. We're going to calculate the wavelength of the photon, right? Well, maybe you should try that on your own. Stop the video. Calculate the energy of a photon. Okay, assuming you have done that. E is equal to HF, right? Well, we're not looking for the frequency. We're looking for the wavelength, right? So we replace frequency with speed of light over the wavelength. So E equals hc all over lambda. So now we are going to plug in, well, we're looking for the wavelength. So let's rewrite this for lambda. Lambda would be equal to hc all over E. And we know that E is 25 electron volts. And I'm going to choose a value for hc that has electron volts, and if you look at your constant sheet by now, you should hopefully realize that's going to be 1240 electron volts times nanometers, so that we can get that beautiful cancellation of electron volts. And so then we're going to have 1240 divided by 25, which on my calculator is 49.6. So that's 49.6 nanometers. Okay, so that's the wavelength of the photon. And so now let's do the electron. This one's a little bit trickier because you see, if you want to find the wavelength of an electron, you have to use our equation that we've been using, wavelength equals h over p, h over momentum. Okay, and because the electron has mass, we can now use, obviously, replace momentum with m times v, right? Now the issue is that we're given kinetic energy. Well, I kind of give you a hint here. We've given you the energy, which is in electron volts here. And we need to calculate the wavelength. All right? So in order to calculate the wavelength, we need to figure out, we know what the mass of electron is, yes, but we don't know the speed of the electron. So I kind of give you a hint here. That 25 electron volts represents kinetic energy. So can we calculate how fast this electron is going if we know how much kinetic energy it has? And I'm hoping you remember your physics from last year. Kinetic energy is simply given by 1/2 mv squared. So if you want to solve for the velocity, that would be equal to 2 times the kinetic energy divided by the mass and the square root of that whole thing. Okay, so go ahead, solve that. I'll stop here for a moment, stop the video, and you solve it. Okay, assuming you did that, there are some typical mistakes that people typically make in this problem. A lot of people will do, 2 times the kinetic energy, and they'll put simply 25 electron volts, and then they'll, like, the mass electron is 9.11 to the power of negative 31 kilograms. And if you plug that into your calculator, you're going to get like a really high value, 7.41 to the power of 15. That, I hope, alarm bells will go off and you're like, I made a mistake. You see, obviously you can't go faster than the speed of light, which is 3 to the power of 8. So that's not possible. You've made a mistake. So what do you think the mistake would be? So the mistake here is the 25 electron volts. What one has not done is convert that into joules. So be very careful that if you're finding the speed in meters per second, which you're trying to do, right, then you need to put your energy in joules. So maybe I'll just do this calculation somewhere. I'm not sure where. Let's do it up here. The kinetic energy is 25 electron volts, but we need to convert that to joules. So in 1 electron volt, there is 1.6 to the power of negative 19 joules. So that's the value that you need to plug into here. So 25 times 1.6 to the power of 19 gives you 4 to the power of negative 18 joules. And that's the energy that you need to plug into your kinetic energy formula. So I would get this answer of 2.96 times 10 to the power of 6, it looks like. So 2.96 times 10 to the power 6 meters per second. That's less than the speed of light, so I know I'm doing things right. All right, and then I'm going to plug that into our deBroglie wavelength equation, and H is 6.63 to the power of negative 34 joules seconds. Mass of electron is 9.11 to the power of negative 31 kilograms. And then the speed I just calculated, 2.96 to the power of 6 meters per second. And now we just need to calculate it. And if I believe I did things correctly, it should be 2.46 roughly to the power of negative 10. So 2.46 to the power of negative 10 meters. And I suppose I could convert that to nanometers. So it's kind of similar to that thing. So in 1 meter, there is 10 to the power of, positive 9 nanometers. Okay, and that will give you 0.246 nanometers. All right, and hopefully I have not made any mistakes in that. Yeah, good. All right, that's example number 12. And we are all done with quantum notes.